In this session, we are going to study simply supported beam with uniformly distributed load. So we have a simply supported beam and there is a uniformly distributed load on that beam, right? So suppose this is a beam and it is simply supported. One is hinge joint, another is roller joint, and there is UDL like this on this beam, and suppose it is distributed on the entire length of the beam, and we have to find out the shear force and bending moment diagram for this case, right? And the intensity of this is W kilonewton per meter, and there is sign convention. We have already written here the sign convention for shear force and bending moment. Now there will be reaction developed. Suppose the reaction at this point is, suppose this is a point RA, the reaction at this point is RB, and the length of the beam is L, right? Now it is UDL, uniformly distributed load, right? And UDL is like a brick which is placed at the surface of the beam. So it has some load concentrated at a point that is called center of gravity of this UDL, right? And that will be W multiplied by L. We have already read in our previous lecture, WL, right? So it is a brick like this, rectangular brick, which has WL as the centralized load, centered at the center of this beam, and it is at L by 2 from A and L by 2 from B, right? And we have to find out RA and RB. So finding reactions, take moment about any point. You can take, say, A or B, you can take A, right? And sum of the moments about hinge joint is equal to 0, right? This equation we already know. Sigma m at hinge joint is equal to 0. So we will be having RA is passing through the hinge joint, so the moment of this RA will be 0. RB, let us take WL as clockwise as positive, so WL multiplied by the distance is L by 2. So we will write WL multiplied by L by 2. This is the moment of the UDL, WL multiplied by L by 2, minus RB is anti-clockwise, so RB multiplied by L, so that will be equal to, you can find out here, WL square by 2 minus RBL, LL will be cancelled out, so you will get RB will be equal to WL by 2. WL by 2. This is the reaction at point B. Now we want to find out reaction at A. We know that the sum of vertical forces will be equal to 0, right? So because the body is in static equilibrium, so sum of the vertical forces in downward and upward direction should be equal to 0. So this will be equal to WL is downward, take it positive, RA is upward, take it negative, RB is upward, take it negative, and that will be equal to 0. So from here you can find out RB we already know, WL by 2, put the value of RB and you will get the value of RA. So RA will come out to be again WL by 2. So we have obtained the value of reactions at 2 points, RA and RB, right? So RA is WL by 2, so this RA is basically WL by 2, and this RB is also, WL by 2. So now the reactions are known to us. Now what we can do is, we can take a cross section from left or right of the section and we can find out the shear force and bending moment of that section, right? So let us say we can take any point, suppose here, and here it is UDL, and there is no point load acting on this, so there is no need to take two sections. We will take only one section, and that will be valid from A to B. So the point will be valid for A to B. So this is our x cross section at a distance x, from the point A, and this will be valid because there is no any other load acting on this beam other than this UDL, right? So now we can find out shear force diagram using the force Fx at point X, and we can draw the shear force diagram, right? So what is shear force diagram? Now we want to find out. Fx, force at X, shear force at X at a distance X will be equal to sum of all the forces to the left of the section, right? So at the left of the section there is WL by 2. Another is this part, you can see here this much part. So this part will be having a point load, a concentrated load here in downward direction, and that will be equal to W multiplied by X. W is the width and X is the length, right? WX. So WX will be the intensity of this load and passing through the center, right? Passing through the center means this will be passing from the x by 2 distance from this side and x by 2 distance from this side. So this part of the beam, this part is a rectangular section of length x and width W. W is the intensity of load, kilonewton per meter. So it is a rectangle which will be having a concentrated load at the center, which is equal to WX, W multiplied by length x, right? And it will be acting at the center, means the total distance x, it will be x by 2 from A and x by 2 from capital X. So this is the WX. So it means there are two forces acting to the left of this section X. To the left of this section X, there are two forces acting basically. One is a reaction, this reaction I am making it somewhat bold so that you can see it very easily. One is the reaction RA, and other is this WX. Right? So, and according to sign convention, because we are taking left side, the upward forces on left side is positive and downward forces on left side is negative. So this WL by 2 is positive upward. So this is WL by 2, and this is minus WX because it is downward. So this is a shear force at a cross section X, right? And this is valid from A to B. It will be valid from A to B because there is no other force in between. So this is the shear force. So this equation can be utilized for at any point of the beam. So we will find out the shear force at the point A and point B, and then we will draw the shear force diagram. So point A, FA, the shear force will be equal to, x will be 0 because we are taking x at point A, right? Starting x from point A. So x will be 0. So it will be WL by 2 because x is 0 here. And FB will be equal to, at FB the length is L now. At B point the x is equal to L. So FB will be equal to WL, so minus WL and plus WL by 2, you will get this will be equal to minus WL by 2, right? At x is equal to L, right? So we have found out x, FA and FB. This is positive at point A, this is negative at point B, and the variation is linear. You can see here there is an x term, means linear variation, a straight line variation. So what type of shear force diagram you will get? You will get this type of shear force diagram. This is our base A, B, this is our beam, and this is WL by 2 in positive direction. At A, this is WL by 2 positive, right? This is WL by 2. Similarly, FB minus WL by 2. This is minus WL by 2. In this direction, we have got it minus WL by 2. And the variation is a straight line from A to B, and there is no change in there is no any load in between, so it will be valid from A to B. So you have to draw just a straight line like this, right? And you will get the shear force diagram, positive here and negative here. This is our shear force diagram. Shear force diagram for simply supported beam carrying a UDL. Is it okay? Now we want to find out bending moment diagram. Bending moment diagram. For bending moment diagram, we will take the movement of all the forces about x-axis, about this x cross section, x cross section. So we have two forces, WL by 2 upward and WX downward. So we have to take the moment of WL by 2 and moment of WX, right? So WL by 2 is at a distance x from the cross section x, and it is x by 2 from WX is at x by 2 from the capital X, right? And according to sign convention, leftward, if it is a clockwise couple, this is positive, and if it is anti-clockwise, then it is negative, right? So we will find out mx, that will be equal to moment of WL by 2 multiplied by x, and that is positive. So WL by 2 multiplied by x, and that is positive, and WX is negative according to this sign convention, minus WX multiplied by x by 2. So this will be equal to WLX by 2 minus WX square by 2, and it is valid between A to B. It is valid between A to B. Entire length it is valid, right? So this is variable, this variation is parabolic. This is parabolic variation. You can see here, this is a parabolic type of variation, right? And one more thing you should know that we will study later on, that where the shear force is 0, the point where shear force is 0, suppose this is the center point where shear force is 0, the bending moment will be maximum at this point. You should know that the point where shear force is 0, the bending moment will be maximum, right? So we can find out MA. So MA will be equal to, MA is at x is equal to 0. Put x is equal to 0 here, you will get this term 0, and MA will be equal to 0 at x equal to 0. Another is MB. MB is x is equal to L. At B point, we have got the length of x will be L, total entire length of the beam. So it is WL square by 2 minus WL square by 2. Again, MB will be 0 at x is equal to L, right? So we are getting MA 0, MB 0 at A point and at B point, and in between we are getting the parabolic variation, and in between you are getting the parabolic variation. And for the time being, you note down that the point where shear force is 0, the bending moment will be maximum. So here shear force is 0 at the center, it means bending moment will be maximum, right? So it means that we can draw now the shear bending moment diagram like this. This is our bending moment diagram. This is a beam A to B. The bending moment must be maximum at this point, and it should be parabolic. So it is maximum at this point and it is parabolic. So this is parabolic maximum, it will go to maximum from 0 to maximum at C, because we know that at the zero shear force the bending moment is maximum, and then at B again it is 0 from maximum to 0, so from maximum to 0, right? And this length at C point, we can find out what is this length at C point, how much is the bending moment at this point, maximum bending moment, right? So this is at the point where shear force is 0, and we know by symmetry shear force is 0 at the center, right? So shear force is 0 at the center, or you can put here for 0 shear force, you can put here, suppose this is equation number 1, suppose this is equation number 1, it is from A to B, I'm writing here this equation number 1, we want that what is the point where shear force is 0. So put this value 0, you will get the value of x where shear force will be 0. So put fx equal to 0 in 1. What we will get? We will get that WL by 2 minus WX should be equal to 0. So this implies x will be equal to L by 2. It means shear force will be 0 at L by 2. And at L by 2, bending moment will be maximum. So put this value in this equation. Suppose this is equation number 2. This is equation number 2 from A to B. It is valid from A to B. So in this equation, find out the maximum bending moment by putting x is equal to L by 2, because the point where shear force is 0, bending moment will be maximum. So now put x equal to L by 2 in equation 2 for bending moment, maximum bending moment, Mmax, for Mmax. And what will be the Mmax? That will be equal to WL square by 2, WL square by 4, WL square by 4 minus WL square by 8, WL square by 8. So this will be equal to WL square by 4. So this will be the maximum bending moment, WL square by 4, WL square by 8, 4 minus 8, this will be 8, WL square by 8, right? So maximum bending moment is WL square by 8, right? So this we have found out. So this length of the bending moment diagram is WL square by 8, right? So at A the bending moment is 0, at B the bending moment is 0, at C where the shear force is 0, the bending moment will be maximum, and the maximum value of bending moment will be WL square by 8. And at A the shear force will be maximum, WL by 2, and at B the shear force will be maximum, WL by 2. So this is how we can find out the shear force and bending moment diagram for a simply supported beam with UDL.